talk about momentum and impulse, let's try to recall what we have learned in chapter 2 kinematics of linear motion. Okay, in chapter 2 kinematics of linear motion, we learned that the area under the AT graph tells us the change in velocity of an object. So I'll bring out something that might be familiar to you. So this is a position time graph, and if we choose to determine the gradient of the position time graph, the gradient will be equivalent to the value of velocity that we see over here. The gradient is increasing with time. That's why our value for velocity is increasing with time. Okay, the gradient for velocity, if you see this gradient, the gradient here will be representing acceleration. And since it's a constant positive gradient, therefore acceleration is constant and positive. Okay, so that's what we have learned in chapter 2. But I want to highlight these two graphs over here because we learned that the area under the AT graph, if you look at this, the area under the AT graph is equivalent to the change in velocity that happens during this duration. So from T1 to T2, let's say you are able to determine the area under the AT graph. This area here will be equivalent to the change in velocity that happens during this same duration from T1 to T2. That's why the area under the graph here, since it's a rectangle, you can get it by taking A multiplied by the width, which is the T over here. Okay, the area is AT, whereas the change in velocity during that duration is just final V minus initial U. So this is what we learned last time, and if you move this equation around, this is how we get V is equal to U plus AT. But now, let me try to generalize this equation a bit to situation where the acceleration is not constant. Okay, right now the acceleration is constant, that's why we are able to get this equation V is equal to U plus AT. But for situation where the area is not constant, then this will not be a straight horizontal line anymore. But we know that from mathematics, to calculate any area under the graph, the area under the graph is just integration, right? Gradient is differentiation, whereas area under the graph is integration. So we can change this equation, generalize it to situations where the acceleration is not constant. When the acceleration is not constant, you can say that V minus U over here is equals to the integration of the AT graph from the start of the event until the end of the event. If you are able to find the integration of the function for acceleration, that integration here represents the area under the AT graph, and therefore it's equals to the change in velocity that happens during the same duration. Okay, so I generalize this equation because I'm going to manipulate this equation to get our impulse momentum theorem. Let's get right into it. So this is our equation just now, where change of velocity is equals to the area under the AT graph. What I'm going to do is I'm going to multiply m to both sides of the equation. So the left hand side will be multiplied by m, so you get m multiplied by v minus u. On the right hand side, you're going to multiply by m, but you're going to put it inside the integration bracket, then it becomes ma, under the function of ma being integrated from t1 to t2. Okay. Right now, if you expand the bracket, then mv minus mu. I believe you see that this is something familiar. M multiplied by v is what we have learned to be called as momentum. So since this is the final velocity, mass multiplied by final velocity will be the final momentum. Whereas u is the initial velocity, so m multiplied by u will be the initial momentum. So this is final momentum minus initial momentum. Okay, so that's what happened on the left hand side. Let's look at the right hand side. The right hand side is still the same thing, but we know that m multiplied by a is actually what you learned from Newton's second law to be your net force. So mass multiplied by acceleration is actually the net force. Okay, so this is P final minus P initial, whereas on the right hand side you can see that this is Newton's second law of motion, ma, so you can change this to become the net force. So now, what we are seeing on the right hand side over here is actually the integration of the net force from T1 to T2. So now we have changed from area under the acceleration time graph to be area under the net force graph. So area under the net force graph, we are going to define this area under the net force graph to be equals to impulse. And as we mentioned just in the first video, impulse, we are going to give them a symbol J. So now we know that the change in momentum is equals to a new value that we define as the area under the net force time graph. And this value that we call for the area under the net force time graph, we call it as impulse. And the change in momentum is supposed to be equals to the impulse. And this equation over here, we call it as the impulse momentum theorem. Okay, so there are two important new messages to be carried here. One is that the area under the net force time graph, we are going to define it as impulse. That's the first thing that we learn. Second thing that we learn is that this impulse over here is going to be equal to the change in momentum that is experienced by the object. Okay, so two important messages to be explained here, and I'll explain it further in the next video.